Well, yes, it's Roger again.
Yes.
Oh, Roger.
Come on, everybody. You're not working hard enough.
Evening all.
How are you doing?
I think there ought to be a few announcements tonight, David. Dave?
Sorry, there's a what?
There's two announcements to make from you, I think, tonight.
Oh.
One is the well done to Johnny and Rachel for getting another publication of a photograph.
Yeah, noticed
and
that.
A happy birthday to Ron Kelly tonight.
Yeah,
today is his birthday.
It is. Ron sent me a message. He's not going to make it tonight, but yeah. So
on the razzle, is he?
I was getting prepared to everybody to sing happy birthday. Julian, did you bring any cake?
Just gone. You almost had it. There's a pancake.
I'm waiting for Kath's pancakes to come.
Oh,
Kath, where are the pancakes?
They might be in my belly at the moment.
Very good at pancakes, Kath. I was impressed with your tossing ability. I've never successfully managed that.
It's years of practice, I think.
Brilliant fun. How are folks doing? You doing okay?
Yeah.
Clear sky here, so that's good.
Have you? Oh, it's
clear. That's why I'm in the dark.
Absolutely peed it down.
Is it?
There we go.
It
was clear, and now it's gone clear.
Well, I managed to get the moon.
Yeah, I saw that. Yeah,
I put it on the Padlet.
What? Mary, good to see you again, Mary.
Hello.
Good to see you again after last month's little tiny technical hiccup on my part.
That's all right.
I have to leave for another meeting, Mary, later, so I'm going to
and so do I as well. So I might not be around for everything.
Do you want to say anything, Mike, before you go? Before we start, just about your events on Thursday?
On Thursday, I can say a little bit. We are having a watch party on Thursday for the Masters of Perseverance rover landing. We are fully booked, but it will be live streamed on YouTube as well, Dave.
Yeah.
But we're also going to be on Astro Radio as well, thanks to Pete Williamson for that. So it's a joint Go Space Watch Virtual Astro Club and Astro Radio meeting. We are up to our virtually up to our 100 limit. We may have a few spaces on the night, so it might be worth dropping an email to us if you want to attend. But we are really up to our limit now, so that's why we haven't allowed any more sign-ups on Eventbrite. So okay. And the other thing is we've got sign-ups from all around the world as well, which is good. Yeah.
Do you want to advertise any more of your events, Mike?
Just bear with me a second. I'll get my slide up. I wasn't quite. Whoops. Get the right thing ready.
Do you want to share a slide?
Not really. Doesn't really matter. I don't think.
Okay.
Yeah. So tomorrow night we have Howard Parkin, I should say, from the Isle of Man Astronomical Society, doing a talk on the dark sky sites in the Isle of Man, which he's been heavily involved with over the last few years. So that should be quite an interesting talk if anybody is interested in setting up dark sky sites for astronomers and the general public, of course. So that's tomorrow night. That's on the 17th. Then on the 3rd of March, we have Sharad Bhaskaran, Mission Director of Astrobotics in Pittsburgh, USA, about their robotic missions to the moon in support of NASA's Artemis program. On the 17th of March, we have another speaker from the United States, Jay Delaney of Leaf Space, who in Washington, and they provide ground segment communication systems for microsatellites. So something rather different on that one. And then on Wednesday, the 31st of March, I'm pleased to announce we got James Carpenter from the European Space Agency going to talk about ESA's missions to the moon. So that should be an interesting one as well. So there are 3 of them coming up at the moment, Dave. Thanks.
Excellent. Okay, thanks, Mike. Okay, just go through my slides as usual. The scribble pad, not many people have been adding to that, but you know, please put some stuff on there, introduce yourself or ideas or anything else you want to add. Post it up there. I say that's my web address /scribble. And of course, there's some great images coming out there on the Padlet, so keep sharing them, because it'd be great to look at all those, and some of those that are in magazines lately will probably be popping up there as well. And again, thanks for all your generous donations. We've got enough in the pot at the moment to keep us going for a while, so but you know, if anybody does want to donate, the web address is there for you. Just the Sky Diary, I think I've mentioned it before, is available. It's on Team Up, so you can download the app, you can take the calendar around with you, and there's 3 calendars now. It's been split into. Steve Tonkin is helping me populate this now, so which is great. So there's 3 calendars there. There's a Sky Diary, which is what to see in the sky. There's space activities and events, so anything that I hear that's happening I pop in there as well, and any space dates, like anniversaries of space flight, etc., etc. I'm starting to populate that as well. So just go to my website /diary and you can download that and carry it around with you. So we had Nicholas Booth a few weeks ago telling us all about Mars. If anybody's bought the book, let me know, because he sent me some stickers, which I have here. And if you like one, I can send one to you. So, it's just a sticker with the 2 authors' names, signatures on. So if you want one of those, pop me a private message with your address, and I'll pop that in the post for you. A couple of people did contact me, and I can't remember one of them. So if you have contacted me before and I haven't sent you a sticker, contact me again so I can send the sticker out for you. Okay. Yeah, we're nearly there. Mike mentioned it earlier. I got my ticket on board. So this Thursday, of course, is the live watch party of Perseverance Mars landing. We're starting at 7 o'clock. The live webcast starts about 7:15. Joint venture with Ghost Space Watch and Astro Radio. So it's going to be broadcast widely on all those formats. And I think the landing is about 5 to 9. Is that right, Mike?
Yes, that's correct. That's what I've seen lately.
But we'll have the live stream from NASA, which starts about 7:15. We've got a great video of the landing to show you before that starts. So,
yeah. So if anybody else can't get on our meeting for whatever reason, there will be lots of other broadcast locations that you can watch the landing as well. So, but when we watched the launch last year of it, it was great fun to watch it and chat together. Yeah.
And so I think the landing will be just as much fun as well.
Yeah.
Good stuff. So future meetings, 22nd of February. We've been invited to attend Clydesdale Astro Society's next virtual meeting, and they've got Paul Money talking about why there are no green stars. Okay, so all the details of the link and everything all on the VAC website. 2nd of March, we've got Dr. David Boyd, who's going to tell us all about imaging Uranus's moons. And the 16th of March, got Catherine Rayner Evans talking about exploring astronomy and space through philately. And then the 23rd of March, it's our first birthday. Been going a year in next month. That's just crazy. Absolutely crazy. And we've got Jim Al-Khalili talking about the world according to physics. So I'm really happy I managed to bag him in the end. He took a bit of pinning down, but I managed to get him in.
Well done, Dave.
Yeah, that'll be looking.
Yeah.
6th of April, hopefully, with the launch scheduled for the 31st of October, Halloween. John Thatcher, who we know from Bedford Astronomical Society some years ago, he worked on the MIRI camera that they're using on the Webb Space Telescope. He's going to tell us all about the Webb Space Telescope. And then we've got 3 other dates we haven't filled yet, so I've had a bit of a rest from trying to find speakers, but if you think of anything, I think the first one we did when we came back after Christmas worked really well when people talked about what they were up to. So it'd be nice to pencil in a few more of those, especially as we get towards April and May. The nights are going to be a bit lighter, so it won't be clear when we do these and dark. So people will be more willing to tell us about what they're up to before they dash out after the meeting. All right.
Dave, you mentioned the anniversary of the anniversary of the VAC. Last night we had a meeting of Barringer Astronomical Society on Zoom, and it was actually a year from when we had a final physical meeting before we went into lockdown. So it's exactly a year to the night that we hadn't had any physical meetings.
Yeah. Well, let's hope there's light at the end of the day. Anyway, we're not going to talk about that tonight. No. So tonight's meeting, we got Mary McIntyre sitting in the wings, waiting to do her bit. We had a couple of weeks ago, we had a talk all about prominent women in the BAA, and I think this is probably a woman who will be prominent in astronomy. Well, is already anyway, and in the BAA. Mary, who's going to tell us all about shadows in space and the stories they tell. So, Mary, when you want to share your screen, if everybody else can mute themselves, please, that would be great.
Yeah, sorry, it's just telling me to stop sharing yours. There we go.
Yeah, that's fine.
You see that?
Throw me off.
Excellent. Oh, thank you for inviting me to do my Shadows in Space talk. This is a real kind of mixed bag of stuff that this talk has evolved since I very first did it a few years ago. And originally, how this began for me was, any of you that know me know that I love to do lunar sketching. And one of the things that makes for a really good crater to sketch is some really prominent crater shadows. And many of us as astronomers will have looked at crater sunrises and sunsets, and also lots of clair-obscur effects. When I became quite well acquainted with this crater Archimedes, because I've sketched it so many times now, I've made 3 models of it, and I feel like I know it really well. But one of the things that I got to thinking when I first started sketching it is, what are these shadows telling me? What do I know about this crater, armed without any other information about its size or the relative height versus diameter? All I know is what shadow shapes are on it, and that is basically where the kind of idea for this began. And it's evolved from there, because shadows are everywhere within space and within the solar system, and I'm going to kind of go through lots of different aspects of that, and some of the maths that we can do, and the maths that has been applied on probes that have visited other worlds to learn more about the landscape that they're looking at. So first of all, we'll start within the Earth system. And the first thing I want to talk about is something that people may not necessarily think of as astronomy. It's more kind of weather, really, but that's crepuscular rays. And the name crepuscular is from the Latin crepusculum, meaning twilight. But these rays are not only visible at twilight, they're just more often noticed at twilight, unless you're me, in which case you notice them 24/7 and crash the car nearly every time you go out, because all you need in order to have crepuscular rays is some sun and some clouds, and luckily we get a lot of clouds here. And all that these things are really are cloud shadows interspersed with the kind of atmosphere being illuminated by sunlight. So sometimes they're not as prominent as others, and it's kind of determined by whatever's in the atmosphere. It could be dust, it could be humidity, they all play a part of it. But this particular picture was taken by my sister, and it so clearly demonstrates that it's the clouds that are causing the darker bands between all of those bright bits. And that's really interesting to me. Now, when we see rays, very often our eye is drawn to the sun side of the sky. And the thing I want to talk about tonight is actually the times when those rays are so bright that they actually transverse across the entire sky, and they actually then meet again, they converge again at the anti-solar point. So these are called anti-crepuscular rays. The minute they pass the zenith and get onto the other side of the sky, they're anti-crepuscular rays. And actually they're more often noticed in association with rainbows, because rainbows, the center of the rainbow is of course also the anti-solar point. So both of these phenomena are on the other side of the sky. Now these are often missed because they're not as bright, but you can still see a full set of them converging there just below the horizon, because obviously the sun is still shining. And this was the best I've ever seen anti-crepuscular rays, and this is more than 360-degree photograph. I love the panoramic function on my phone. It's so good for atmospheric optics, because these sorts of things are way too big to fit in the field of view of an SLR. But you can see that they're converging here and then arching all the way across to the other side of the sky. And these are really quite something to see. And I was really fortunate on the way back from Barcelona a few years ago to look out of the aircraft window and notice an entire full circle set of these as viewed from the air. And what was even more awesome is when the clouds parted, you could actually see the anti-solar point, which is just an empty bit in space, yet all of these rays are fanning out from it. And it's just absolutely mind-blowing to me when the story that these shadows are telling basically is that the sun and the distances that these rays are traveling to converge at the solar point and the anti-solar point is absolutely huge. The reason we know that is because those crepuscular rays are actually parallel, and this is demonstrated by a photo shamelessly stolen off the internet, but it's of a square tunnel with all of these rails and beams on the ceiling, which really perfectly demonstrate the effect that those parallel lines meeting at a point infinitely distant. And even though you know that this tunnel must be the same size all the way along, otherwise you wouldn't be able to walk through it all the way, when you just kind of forget about that and just look at the shapes you're seeing, you can see that they're fanning out. And if you want proof of that, this is an Apollo spacecraft photograph where you can see that those cloud shadows are actually in a straight line. And it's just the distances involved here are so massive that the rays actually look like they're converging at the opposite sides of the sky. So next time you notice crepuscular rays on the sun side of the sky, just have a look on the other side of the sky as well, because these may be something that you've not noticed before. And if ever you see a rainbow, just have a look if you can see the stripes, because sometimes you can get a full set with a rainbow and it looks like a cartwheel. They're on the Atmospheric Optics webpage, they're sometimes called spokes of a wheel as well. So that's something possibly new for you guys to look out for. But also talking about shadows is the belt of Venus phenomenon, and this is also on the anti-solar side of the sky. And generally when the sun is setting, because of the just basically the way sunlight interacts through more atmosphere, you end up with preferential scattering and the sky goes red. But on the opposite side of the sky from where the sun is setting, you very often get this really nice, slightly more muted pinkish, peachish coloured band. And the colour of that will be again determined by atmospheric conditions. So if it's very dusty, very humid, if you get a very prominent belt of Venus, it's usually a sign that the seeing isn't going to be as good, but it does look really striking. And equally, you get this before sunrise, but over in the west as the sun is rising. The bit that's really interesting, though, when you notice that, is this band of kind of grey across the bottom, and that is actually the shadow of the Earth being cast onto the scattered light beyond. And this is a time lapse that I did from Lyme Regis when we were on holiday there. So as the sun gets below the horizon, the grey band starts to rise. Then as the sun gets lower, the band gets higher and higher and higher until eventually the whole sky is engulfed by the shadow and we end up in nighttime. And equally, you have it in reverse during sunrise in the morning. If you look in the west, you'll see that band getting smaller and smaller and smaller until the sun gets above the horizon. One of the things that we learned many, many years ago by studying that shadow is that it isn't straight. So we know that the Earth is round. And we're going to come on to that again in a minute with eclipses. And eclipses, we can't really do shadows in space without talking about eclipses, because they are obviously one of the things that we study shadows a lot during. And there are different things going on during solar and lunar eclipses. Now, first of all, oops, I've gone the wrong way. For those who don't know, you guys do know this already, but for those who don't know, during a solar eclipse, the moon is passing between the sun and the Earth. Now, obviously, this is not to scale by any stretch of the imagination, because the distances are way huger and the size differences are not the same. But what tends to happen then is the path of totality during a solar eclipse is where you see basically the total solar eclipse, where the whole of the photosphere is blocked out. And that is a really small, narrow path that kind of passes across the Earth. Now, eclipses happen a couple of times a year, but generally they may not be completely total, and also they very often happen out to sea or just somewhere not habitable. So we don't really get the opportunity to view them that often. You do get a partial eclipse if you are in the penumbra. So the darkest bit of the shadow is the umbra, then outside of that is the penumbra. And this is also not to scale because the amount of space on the globe that those shadows take up is actually quite small, but it kind of gives you a vague idea of what's going on. And I only found this out last week, but eclipse chasers are sometimes called umbraphiles because they're chasing the shadow, which I think is an awesome name. Now, when we look at a total solar eclipse, you can see that this was a picture. I was lucky enough to be in America in 2017, as most of my astronomy friends seem to be. And you can see that as the moon is kind of passing in front of the sun, more and more of it is kind of disappearing, and then eventually you end up with totality, the diamond rings either side, and then it starts to pass away again. And it's very awesome that we live in a situation where the moon is 400 times closer than the sun, but they are 400 times difference in size, so one completely eclipses the other, but only when it's at the right point in its orbit, because the moon's orbit isn't perfectly spherical, so sometimes you get an annular eclipse. But as far as I'm aware, we are the only planet in the solar system that has this chance alignment that means that we get the opportunity to view this from Earth. Now, obviously, this isn't actually a shadow that we're looking at here. The Earth, you've got kind of, you just see it on this picture, but all my shots were handheld and manually bracketed. I didn't quite get a shot that was bright enough to look at Earth shine, but the moon is fully in the shadow of the Earth there, and you basically can't see very much of it to the naked eye. When you actually look at during a total solar eclipse, the shape of the corona is different whether you're at solar minimum and solar maximum. And this is, although this is not technically the shadow as seen from Earth, this is really interesting to observe. And basically, when we have solar minimum, which is what happened in 2017, you generally get a more focused streams of the corona. And that's because of magnetic differences, and sunspots and active regions are all basically causing this whole kind of chewing up of the magnetic field lines. So when there aren't that many sunspots, the solar wind is more energetic in certain regions, and it can therefore cause these big long coronal streamers. When you get something, when a total solar eclipse, when you've got solar maximum and therefore lots more sunspots, lots more active regions, because of the differential rotation of the sun as well, all of those magnetic field lines have just become an absolute tangled mess. And as a result of that, it kind of disrupts the flow of solar wind. So you end up with a more uniform dispersion during solar maximum. So that's one of the things that this is helping to teach us, is what's going on with the sun's magnetic field during those times. Now, we're lucky now that we have spacecraft that have coronagraphs on them, so we can study the corona at all times. But back in history, we didn't have that luxury. Now, if you actually, this is a model that I have of the Earth and the Moon, and this is what's actually going on during a solar eclipse. And you can just see, this is just me obviously recording it on my phone while I was trying to move it, but you can clearly see, just using a lamp as the sun, you've got the umbra there and the penumbra around the outside. And you also see there that as viewed from one spot, you get a kind of distorting of that shadow when it's kind of round to the sides of the globe. So that is what's going on, not to scale obviously, but it's the shadow passing across the surface that is actually going on during a solar eclipse. And this is actually a video of that. This was the 2017 eclipse as viewed from space. It was a really amazing eclipse because it was basically covering pretty much the entire landmass of the USA. So it must be the most viewed and the most photographed eclipse in history. I mean, I hardly know anybody that wasn't there. Another thing with shadows is something that was more recently discovered, and that is shadow bands. I'm going to move this video on a little bit. It's in a format off Wikipedia that I couldn't edit to cut this down. But when we get close to totality, you can see this kind of rippling shadow effect if you've got something white on the surface. We were looking after so many cameras and trying to just observe the eclipse ourselves because it was our first one. So I had white things on the floor, but completely forgot to look at them in the excitement of how fast totality seems to happen. But this, again, is because the sun at this point is coming from a very small region. The sunlight is coming from a small region, and it's basically atmospheric turbulence that's causing this effect. And they're saying this is something that was only discovered fairly recently in astronomical terms. So if you ever do get the opportunity to go to a solar eclipse, that's definitely something worth looking for. And Mike Frost, I know, was lucky enough to be at the solar eclipse earlier this year, and he could see these shadow bands, but unfortunately the video didn't really pick them out very well. It's on his YouTube channel, though. He could see them, and his excitement that he could see them was enough for me. I enjoyed watching the video. Now, in terms of a lunar eclipse, this is something that is more us actually looking at a shadow. And the reason for that is because at this point, Earth is on the other side. So the Earth is between the sun and the moon. Because the Earth is so much bigger than the moon and Earth's shadow is therefore huge, the moon passes through that shadow. This doesn't happen every month because there is a slight tilt in the orbit. The moon is not or the Earth is tilted, and there's a slight inclination in the lunar orbit as well. So it has to kind of be aligned properly. But these can only happen during a full moon. I didn't say that a solar eclipse only ever happens during a new moon, but a lunar eclipse only ever happens during a full moon. And these take place over a much, much longer period. So a total solar eclipse, the totality bit is usually a couple of minutes, at maximum about 6 minutes. But if you've ever watched a lunar eclipse, it just takes hours and hours and hours and hours and hours. And that's fine. They're really interesting, but it's a very different kind of observing. So you've got the umbra there. So if you get a total eclipse, moon has passed into the umbra of Earth's shadow, but the penumbra is huge, so we get a lot of partial eclipses. And sometimes if you get just a partial penumbral eclipse, it's really difficult to actually see anything at all other than a hint of darkening just in one little region. This was in 2015. We had a total solar eclipse, and it was a perigee moon as well, so it was perigee super blood moon or whatever crazy name the press gave it. But what was really unique is that we had an actual clear night here from the start to the finish, and I imaged the entire thing. Frustratingly, I actually had Radio Oxford in the garden with me, so I was trying to control this camera and the one in the observatory whilst doing all of these interview bits, which was a great experience, but it meant that I wasn't able to focus on the imaging very well, so consequently the pictures I got were not the best. Partly here, when I changed the camera battery, things got nudged a little bit, but it just shows you there that you've got the moon starting to pass into the shadow, and then when we get to totality, rather than just completely disappearing, the moon then looks really kind of red or orange, hence the name blood moon, which I really detest, but that's what it tends to get called by the press because it's a catchy headline. And the interesting thing there is that is basically because of Earth's atmosphere. If Earth had no atmosphere at all to kind of scatter that light, then the moon would be completely invisible during totality. And it's really weird because when you actually watch this, you can see the moon get smaller and smaller and smaller, then suddenly it's all just visible again, and it's really kind of messes with your head a little bit. But then you come out of totality, and then you obviously get the moon moving away and becoming illuminated again. This was another thunder moon partial eclipse. They do love to name the Native American moons, and I love when they say, oh, it's a full moon eclipse. It's like you can only ever get an eclipse during a full moon, but they don't care about that. It's just clickbait. But this was a more in focus set of images, and we only had it when it was rising, so we didn't get to see the whole event, but you can just see how awesome this looks, and it must have been a real source of mystery to ancient astronomers. And this was the pictures that I took from the observatory on that previous occasion. The focus had got knocked, and by the time it was totality, the moon was so faint that I couldn't get focus again. So I was always not in love with these pictures, but it just shows you the colour there. And you can quite often get like an ozone bit that's more of a bluish colour on the edge. And just to show you again with my trusty model, this is what's going on here. You've got the moon passing, the sun is off centre here because otherwise I couldn't get it in shot. But as the moon passes into that shadow, you can see that there is a penumbra first of all, and then there's a harsher line of an umbra. You got to love polystyrene balls. It's just fantastic for doing this sort of imaging. So in terms of the stories told, what have eclipses told us? Well, first of all, solar eclipses, as I said, allowed us to study the corona and therefore could infer what was going on in terms of the magnetic field during solar maximum and solar minimum. And I can remember it's within the last 10 years that we first actually even found out that there were like opposite poled magnetic field lines running from sunspots in sunspot pairs. So, you know, it's a relatively new understanding of what's going on with active regions. In 1919, Arthur Eddington tested the theory of general relativity using a solar eclipse. I can't remember the exact details of how they did that, but they did it, and it proved that general relativity was correct. In terms of lunar eclipses, once again, that shadow that is seen obscuring the moon is clearly spherical. So even Aristotle stated that the Earth's shadow was circular. So we knew that the Earth was round. This is no news to us, but we know that. And the other thing as well, that the ancient astronomers were so intelligent, Aristarchus actually used lunar eclipses to estimate the distances to the moon. So yeah, absolutely amazing stuff that was found out way back. Now, the exact colour the moon goes depends on atmospheric conditions. And as I said, it would be completely black during totality if we didn't have an atmosphere. But before the event, it's impossible to say how red or how dark brown the moon will go. And there is actually a scale that this is measured on. I think it's a scale of 1 to 6, if I remember rightly. Sometimes it's bright orange, sometimes it's a deep red, sometimes it's almost dark brown. And it's really all determined by atmospheric conditions at that time. So an eclipse can still tell us something about the atmosphere just based on the colour that everything looks. So eclipses are awesome. I don't think I will ever get tired of observing them. I'm just going to briefly come on to some terrestrial shadow stuff because it's going to be relevant to what we're going to do on the moon in a moment. Now, shadows on the Earth, as the sun gets lower in the sky, shadows get longer, and that's the case on any celestial body. If you've got a feature casting a shadow, as the sun gets lower in the sky relative to that feature, the shadows will then elongate. And one thing that was a project for astronomy GCSE, but I remember doing this at school as well, is to do a shadow stick experiment. And there are a few things that this tells you, but basically what you do is just put something of a known height, in this case it was a 1 meter ruler, just use some whatever you have to keep it in place, and yeah, we just had some tarpaulin down on the grass here, then just measured the shadow at regular intervals. We were really thwarted here. We chose a day that was very cloudy and the exact times of all of the measurements were not when we wanted to get them, but basically over a period of time before the cloud finally completely obliterated the sun, we were able to at least see that the shadows are getting longer, and you could actually measure this. We just used chalk on a tarpaulin to do this. One of the things that this will tell you is the time of local noon. Now, time, if you are on the Greenwich Meridian time, then noon, as in Greenwich Mean Time noon, will be actually at noon. But so that's a kind of standardized thing across the whole UK. The actual definition of local noon is the time at which you get the shortest shadow, and that varies by about 15 to 20 minutes across the width of the whole UK, depending where you are, like east to west. And so it will tell you what time your local noon is. Now, this used to be important to people, but now obviously trains wouldn't run very well and buses wouldn't run very well if we all had our own definition of noon. So obviously everything has to be standardized. At that particular date, the time that we did the measurements, our local noon was, I think, about 12 minutes after noon. I can't remember now, but the shadow at the shortest point on that particular date was 88 centimetres. Now, if you are somewhere equatorial at the height of summer, you will have no shadow at all. There's only one day of the year, I believe, that's a no shadow day, and there are only certain places within the within the world that is possible. I think it's actually at the tropics. I may be wrong, but there's a couple of places on Earth where for one day of the year you get a kind of zero shadow day, as it were. That doesn't happen to us, so you can do this experiment any day during the year that you get a clear sky in the UK. But what we did is just did this 1 centimetre ruler, and we had the shadow at local noon. There's a really interesting piece of maths that you can apply here, and that is tan is opposite times adjacent. Tan of the angle is opposite times adjacent. So this is a little bit of trigonometry that we did in GCSE maths or O-level maths, if you're older than I am. And basically what we did was did some calculations to try and figure out what the sun angle was at local noon and then again at a time later on. So what does opposite and adjacent mean? Opposite is basically the height of the feature, and adjacent is the length of the shadow. Now, you can use a 1 centimetre ruler to measure a comparative length. If you are stood next to a tall tree, you can measure the height of a 1 metre ruler, then measure the length of the tree and do a little bit of division, and you can figure out the height of something tall. And that's great if you have the ability to stand somewhere with a 1 metre ruler. But when we go and explore the solar system, particularly with probes, we don't have the ability to put a 1 metre ruler on the moon's surface and figure that out. So this is an equation that is really, really useful, and I'm going to go through some maths in a minute with you to show you how to do that. So opposite is the bit that's opposite the angle that the sun is making, and adjacent is the length of the shadow. So just putting that in simpler terms. So the tangent, all you need to do is press the tan button on your calculator or type it into Excel. You don't have to know how to do that, but basically on this occasion it was the tan of the sun angle was 100 divided by 88. I love using a 1 metre ruler because it means you've got a number that's easily divisible, and that meant that the sun angle at local noon in our garden in Oxfordshire on that date was 48.7 degrees. When we did the calculation again a little bit later on at 13:45, the shadow had elongated in that short time to 110.5, and that meant that the sun angle was now 42.1. Now that is an equation that you can rearrange, because one thing that we know very, very well within the solar system is the orbital mechanics of everything. And if you know what the sun angle was at the time a probe has taken a photograph of another world, you can apply this maths to calculate the height of the features that are casting shadows, and this has been done widely throughout the solar system. So let's just park the maths for a second, and let's just go back to this crater, Archimedes. This original sketch that I did was done from a photograph by Craig Howman, which is fantastic. And I was mentioning that I was intrigued by what the shape of this shadow was telling me. Now, if something is taller, it's going to cast a longer shadow. We know that for a fact because we see it all the time in our surroundings here on Earth. When you look at a photograph of a crater, particularly under a high sun angle, like near a full moon, it looks like all of the crater walls are the same height, but the shadows are telling you something very, very different. And even the crater itself is casting a shadow onto the lunar surface, and you've also got a shadow being cast actually onto the floor of the crater. So without actually knowing the diameter of this crater or the relative height versus diameter of this crater, if we were to just kind of stand in the middle of this crater and look to that skyline there, this is just a very crude sketch, say not to scale at all, but we know that if we were standing somewhere that gave you a good view of the whole side of the crater there, this is the sort of shape that the skyline would have. And we know that there must be a tall bit here to cause this like longer shadow here. We know there has to be a dip in order to get these dips. So just in a very crude representation, that's the kind of thing that you might expect. Now, if we're looking the other way, the sun is now behind us, so there won't be any shadows visible on the floor of the crater, but you can see there are lots of kind of foothills and interesting little things going on there where the walls have slumped down. And basically, this is the sort of skyline that side of the crater is going to be showing us. So even without any mathematical information or prior knowledge of the moon, just studying the shadows of something like that can really give us a better understanding of the terrain that we're dealing with. That said, it's very important that you look at stuff under different lighting angles. And the reason for that is because when the sun angle's quite low down, some of these features can start casting these extremely long pointed shadows. I did a sketching workshop with this crater today, and that was really good fun, teaching children to actually look at this and think this, what looks like a smooth crater wall, clearly has something here that's casting this long shadow. This picture here is the Montes Caucasus Mountains near a first quarter moon, and again, these really long pointed mountain shadows. And that gave rise to a lot of space art that is of this vein. And I really love these sort of space art things, but they can, it's important when you're looking at shadows that you do so under different lighting angles, because that can give you a very false impression of what's actually going on. This is just a sequence of pictures that were taken in April a couple of years ago. And you can see that when the moon is kind of near first quarter, you've got loads of definition along the craters near the Terminator and just off to the side there as well. Once you get a bit more illumination, you're seeing lovely shadows around these mountains. But already, once you start getting into the gibbous phase, all these crater shadows have now been almost obliterated. You can barely see the highland regions here anymore. Once you get to a full moon is great for looking at the contrast between the color differences on the Maria and the really big impact craters like Tycho. You can see those ejector rays and stuff like that. But in terms of looking at crater shadows, it's absolutely terrible because they've all but vanished. And this is an example of the difference that having a half-lit moon versus a full moon can make to the lunar landscape. I really struggled to identify these craters, and this is a photograph that I took myself. This was done with a Liverpool telescope, and if it hadn't been for Theophilus having this white ring around it, I was genuinely struggling to get my bearings on this picture, even though I knew that it was the same portion of the moon. And equally, the Ptolemaeus trio, one of my favorite crater trios, all but obliterated when you get a 95% moon. And that's my sketch of this region. Such a beautiful region to study. So it's really important that you do look at different lighting angles. And this is a couple of sketches that I did based off photographs taken by Dave Galvin, taken 2 hours apart. And you can see the evolution of the shadows on Ptolemaeus here. There's a massive difference in that 2 hour period. And you can also see the fact that there's this shadow here tells you that the floor of the crater is kind of sloping downhill towards the other crater wall. Now, I made a model just without doing that. This is again not to scale in terms of height versus diameter, but I wanted to make a model so that I could demonstrate a crater sunrise and sunset in a short amount of time and actually show how those shadows actually evolve as the sun angle changes. Because in real terms, crater sunrise takes place over several hours. Then depending where the crater is on the lunar surface, it could be a couple of weeks before you end up with the moon setting on it again. Days last a really long time on the moon. So this basically is a video using the sun as a light source, but with me moving the model, and you can see how those shadows change a lot once you get a high sun angle. And as the sun now sets on the other side, you can start to see that these shadows begin to get longer and longer and longer. And then the only bits that are still illuminated once you kind of get the sun at a very low angle are the really high points of the crater. So that's a crater sunrise and sunset kind of demonstrated in a really fast time. So let's have a look at the Theophilus. I really struggled. It's like that fruit. Is it called Physalis? Theophilus crater trio. Now, just to put this into context, These craters are huge, and that's why they're very good to observe from Earth, because the moon is actually a really long way away, and it's really good that we have these big craters because we can get great high-res photos of them without having to go out and be part of the lunar orbiter team. But if we were to superimpose this trio on the UK, it would stretch pretty much from North Yorkshire coast down into Wales. So it's a pretty big crater. And if we were to superimpose it over London to Oxford kind of scale, then this is huge. It's a really, really big crater. Now, we can use the length of the shadows here. This photograph was taken by Alessandro Bianconi, taken back in 2011. It's a phenomenal picture and really gives you some very crisp crater shadow definition. Now, I mentioned before that we could use the tan of the sun angle equals opposite divided by adjacent. Now, obviously, we can't stand there with a 1 meter ruler on the surface. So we basically just, this is the tan of the sun angle. And just to get those terms in place again, and the opposite is the height of the feature, so that's that bit there, and divided by adjacent, which is the length of the shadow. And from a photograph, you can just literally measure the shadows. Now, we do know the sun angle. As long as you know the exact time and date that the photograph was taken, we do know the sun angle. So we can rearrange that equation to be opposite equals tan of the sun angle multiplied by adjacent. So that means we can calculate the height of the feature by tan of the sun angle multiplied by the shadow length. And I'm going to just talk you through a crude process that I followed to do this. Now, you can do this more accurately using the Photoshop measuring tool. I am not a mathematician, but I wanted to just put this across in a fairly simple way that makes it easy for people. So I like maths that's easy because maths is not something that comes easy to me. So wherever possible, I will use something that is going to give me an easy divide or multiplication. So what I do is I just open this picture on my laptop and I zoom into it until the entire crater diameter is 10 centimeters across, or 0.1 meters. So that's one bit of the maths that's really simple because it's just a factor of 10. The next thing I do, obviously without changing the zoom, is just measure the length of the shadow. And in this case, that was 0.02 meters of the central peak. I'm keeping it in meters because that's the units that are going to be used in the equation. So as well as the central peak, you can measure the length of the shadow cast by the crater wall. And I just chose this particular bit, and that came out at 0.03 meters. So the next thing you then need to do is to use the Lunar Terminator visualization tool, which looks something like this. And you can download this for free. And I've actually got a kind of a description of step-by-step how to do this. If anybody wants it, I can email it out to you later. And on there is a download link for the Lunar Terminator visualization tool. It's a crude tool, but it's incredibly useful. So you open it up and you just put the time and date at the top here, and then you've got the Lunar Terminator, and then down here you've got all of these different boxes. And basically, once you've inputted the time, you can actually just zoom in a little bit by putting the zoom down here and then clicking on texture. I don't know why texture zooms you in, but it does. What you do is you just use your mouse, and you will notice when you do this that the sun angle is different on the crater edge compared to the central peak. So you've got to be quite accurate with where you point the mouse when you're doing this. But on for the central peak calculation, I just hovered the mouse at the bit where I thought was the tallest bit of the central peak. And down here, it will tell you what altitude the sun is at from that feature. So this is a really useful tool, and it's actually quite easy to use as well. I ignore most of the other stuff on the screen. All I'm interested in from this tool at this point is what the sun angle is. So at this time, the central peak sun angle was 3.7 degrees. So I'm just going to work through the maths with you. Just to show the difference there is actually a massive difference. The sun angle at the crater wall was 4.6 degrees. So you can see that there's a big difference between the sun angle. And that's purely because this is a huge crater. So obviously the sun angle is going to be different between the two of them. So just working through this, to do this in terms of a crater diameter, you need to know the diameter of the crater. If you don't have that information, you will need to know the pixel kilometer ratio of whatever camera it was that took that picture, and make sure it's not a cropped photograph so that you're still getting an accurate representation. But luckily, a lot of the big crater diameters are published online, so you can just use that as a starting point. And the diameter of Theophilus is 110,000 meters, so it's 110 kilometers across. Now in our photo it's 0.1 meters, so that helps with one step of the maths. So we then need to convert the actual shadow that we've measured into a realistic actual shadow length. Now the shadow measured 0.02 meters on our screen, so to calculate that length, we're just scaling it up basically. You just take the diameter of the crater, divide it by whatever the scale is that your fit picture is, and then multiply it by what the length of the shadow was on the picture that you've just measured. And that comes out that the shadow of the central peak was basically 22 kilometers long. And it's absolutely mind-blowing when I've done this calculation for many, many craters, and you're seeing crater lengths on Ptolemaeus that are like 130 kilometers in length. And it's just insane to me that the shadows are as long as they are, but that's what they are. So once you've got that, the actual maths using the formula that I showed you before, we know what the sun angle is because it was 3.7 degrees. So first of all, you need to convert that into radians because that maths only works with radians. The way you do that is pi divided by 180 multiplied by the angle in degrees. And I, of course, do all of this in Excel because I'm terrible at maths. So once you've got everything set up in Excel, you can just plug different numbers in. So once you've figured out how to type this into Excel once, you can just reuse it over and over again for different craters. But that basically brought out the angle as 0.0646 in radians. So we can move on and plug that into the rest of the formula. So we know that the height we're trying to measure is the tan of that sun angle times the shadow length. So we know that the sun angle is this. So it's tan of this multiplied by the length of the shadow, which was 22 kilometers or 22,000 meters. So that means the height of the central peak of Theophilus was 1,423 meters. That's all the in-depth work through of maths that I'm going to do with you, because I know maths isn't everyone's cup of tea, but I do have the step-by-step of this if you want me to send it to you. So the calculated value that I got here was 1,423, and the published height of the central peak is 1,400. So I was pretty pleased with that because there are a number of caveats that I'm going to explain in a second. The wall came out slightly more inaccurate, and there are several reasons for that. So the calculated height was kind of 2.6 kilometers tall, published is 3.2. Now we took one measurement here. This is just one measurement from this one bit of the wall, and you can see from this shadow that this crater does not have a uniform wall height all the way around it. So basically this was never going to be fully accurate doing it from just one point, but I'll talk about how we can improve that accuracy in a moment. So some caveats just to explain why there are some differences here. First of all, when you look at a fairly complex crater or even a mountain, how do you decide where the feature starts and finishes in order to measure your diameter? How do you know where the shadow starts and ends? Because the shadow may well be kind of morphing off into a different shadow or a lower lying part of land. So it can actually be incredibly difficult to accurately measure those things. And it sounds like it would be easy, but it really isn't. An example here, if you look at Albertagnus, the shadow of the central peak is kind of morphing into the shadow from this craterlet. You've got all of these different bits here. You can see that there are slump terraces here because there are bits still illuminated on this picture. Do you measure from there or do you measure from there? It's really hard to know. And on a crater the size that these are, that makes a difference. Tycho is another one. You can see all of these slump terraces here, and you've got a deep shadowy bit there. Do you measure from that bit to that bit or from that bit to that bit? It's really hard to know accurately where to measure it. Also with the mountain ranges, I haven't successfully calculated any mountain range stuff yet because I don't have a crater diameter I can work from. And yes, you can look online and find out how many meters in length is the Caucasus mountain range on the moon. But what it doesn't tell you is whether it's including measurements from this foothill here, whether it's just talking about these bits, whether it includes all of this stuff up here. And we're talking about double the length if it includes those little highland bits there. So it's really, really difficult to know exactly what kind of size thing we're talking about. Also, I didn't realize this, but it's very difficult to actually find an accurate size published online. There's a lot of stuff published online, but very often it's based on papers that people have published using the shadow method, and you can't access all of the paper to see all of the information. Sometimes things are just wildly rounded up, and if you go to Wikipedia, you'll see two conflicting values in the same article for the same crater. So I try to use Wikipedia if I have to, but I will try and find something from NASA or from the Lunar Reconnaissance Orbiter team, or just something from a more reputable source to try and find those sizes. Also, we saw that crater walls are not uniform, so taking a measurement from one point is never going to give you an accurate answer. We also know that the ground inside a crater is not perfectly level, and although the shadow, the highest point is going to be a 90-degree kind of angle in order to create the shadow. So the height in terms of 90 degrees to the ground is okay, and it has to be a right angle triangle in order for this maths to work. But what does make a difference is if the crater floor is sloping uphill or downhill, the shadow is going to get foreshortened or lengthened, so you're going to get an inaccurate measurement there. The biggest one as well, when you're talking about craters that are really big, is the fact that the moon is not flat. The moon is a sphere, and I did a demonstration to show the effect of this using a Christmas tree bauble. I took a piece of post-it tape that was 8 centimeters long, and I marked it with ½ centimeter increments, and I wrapped it around my biggest Christmas tree bauble, then held up my ruler to it and took a measurement, and that 8 centimeters ended up being foreshortened to 5.6 centimeters. Now, obviously, the craters are not the size of the entire moon here, so this is an exaggerated impact, but it is still going to make an impact. And also it's going to be more of an issue if you're photographing stuff that's near the limb, kind of in the libration zone, because the distortion is going to be greater there. So to get a more accurate answer, kind of focus on craters that are somewhere in the middle as well. So also measuring is very, very difficult. How do you know that you're measuring from the very top of the peak? You've also got to be careful that you're keeping in mind the angle of the sun in terms of the direction that the shadow is, because if you measure the shadow at an angle instead of in a straight line relative to where the sun was shining, you're going to get an inaccuracy again. The other thing that you should definitely be doing is not taking one measurement. So you should be doing this at different sun angles. So in terms of the central peak, for example, do it over an entire crater sunrise and take different photographs, and then measure all the way through a crater sunrise, and then do the same thing during a sunset and measure the crater shadow from that side, and then average it. Equally, if you're doing a crater wall measurement, you should be taking points at all different bits around the crater wall and averaging them, and doing that all the way through the different parts of the month, so that you're different parts of a crater sunrise, so it's going to give you a more accurate answer. So it's a lot of work and it's a lot of maths to get super accurate, but you know, you can see that you do get the right ballpark doing it with one. Now this was crater Albertagnus, and I like the face in Albertagnus, that's why I chose this picture, but I measured the longest part of that, and the calculated height of the crater wall that I got there was 4.33 kilometers, and the published is 4.4. I'm frankly astounded by this, because you can see that clearly it's not that tall here and here, and this is obviously just one measurement, so I think I just lucked out that the average is close to somewhere where this long shadow was, because there are clearly bits here that are much shallower than that was. I did the central peak of that as well, There's a little bit more inaccuracy here. It's like 1.9 that I calculated versus 1.2 kilometers, but that's because I wasn't sure where the shadow finished because it goes off into this craterlet, and I think I assumed that it went all the way to the end there because it looked like it wasn't pointed here. But again, there's going to be inaccuracies there because it's gone up and over a kind of craterlet wall. I also did the same thing using this photograph of Tycho by Alessandro Bianconi, and basically the crater wall height that I got here, I calculated 4.3, but the published is 3.2. But again, that was contradicted in its own article on Wikipedia. The central peak, however, although it's more complex and there's lots of different bits to measure there, whatever measurement I did, I kind of lucked out again and managed to get something that was pretty close to the published crater height. So that just shows you that even just using my very crude method can get you some answers that are somewhere within the right ballpark. So, Crater Tycho, we're done with the maths for now. I'll mention it again in passing, but we're done with the maths part. When we look at Tycho under a full moon, it looks kind of uninteresting, to be honest. And when you see Tycho and a full moon, you see those amazing ejector rays, and you expect that Tycho would really stand out. And actually, I find it hard to pick out Tycho from all of the craters on the moon. It just so happens that's the one that has all those ejector rays. But when we look at that picture of Tycho, you would not believe that it was this beautiful. This is sunrise over the central peak from Tycho, taken by the Lunar Reconnaissance Orbiter. Now, I was in the audience at European Astrofest a few years ago when the Lunar Reconnaissance Orbiter team actually showed these pictures for the first time, and I can't do a shadows in space talk without showing this pure shadow porn because it's just beautiful. All the little foothills here casting shadows. This is a picture that I really want to sketch from in pencil because it's just beautiful. Have a look in the very center of there. If this picture wasn't impressive enough, they then zoomed in to the point where they've got a photograph of a shadow of a boulder that's sitting on top of the central peak. So this boulder is probably about 400 feet across, and it's literally just sitting on top of the central peak, and you've got all of these smaller boulders casting shadows as well. I cannot tell you how much I love that we live in a world where this photograph is possible and just out there for us to enjoy and look at. So beautiful. Now, this is a good point to talk about something that's very important when studying particularly surface features based on photographs. That is the crater dome illusion. And the best way to demonstrate this is with my cheese grater. So one side of the cheese grater here is obviously domed because it's the bit that grates your cheese. The other side of the other picture that I've got on this screen is not the dome side. It's the bit that I am calling a crater. If you don't know which is which, it can be quite hard to guess. So you may have guessed that this was the dome side. I think it looks a bit more domey than this bit perhaps. But what's really interesting, if you flip that picture round, these are the same pictures but just flipped the other way round, and suddenly the part of the crater that looked like domes before now suddenly looks like craters, and the bits that looked like craters before now look domed. And this is something that's really important to keep in mind when studying photographs taken from orbiters or probes from space probes, because you just don't really know whether your eyes are tricking you. This is Barringer Crater, and that's the picture we're used to seeing of Barringer Crater. If you turn that through 180 degrees, it looks like a hill. It's just the way the brain tricks you with certain lighting angles. And this is applicable on the moon. One of these features is a lava dome on the moon. The other is a crater. And they are side by side. These, I think they are LRO pictures again, but this was from an article on earthsky.org. And it's really difficult to tell which is which. The scale here, this is 500 meters. So this is a pretty high res photograph. put you out of your misery, that's the dome, that's the crater. There is nothing I can do to make my brain see that as a crater. It just looks like a Madonna's bra. It's just pointing upwards. It really just doesn't look like a crater to me. But if you flip this upside down, the lava dome now looks like a crater, and that still looks like a dome to me. But it's interesting because the way around I see it is sometimes the opposite to the way around my husband sees it. It really just depends on the way your brain sees it. It's like one of those trick 3D puzzles where your brain keeps changing it around and you don't really know what you're looking at. So it's worth bearing that in mind when we now just venture out and go and have a quick look at some stuff on Mars. A couple of Mars was at opposition. Dave took some way better pictures than I did, but this was my first ever surface feature photograph of Mars. And this is just, I can't possibly not show a selfie of the Mars rover shadows while we're talking about shadows in space, because again, the fact we live in a world where a robot on the surface of Mars can take a selfie of its own shadow and beam it back to us here on Earth, that's just absolutely crazy. So my cats are normally not allowed in the Zoom room anymore, but she's managed to open the door, so apologies if I've got a tail swishing in front of my face. This is Mars Opportunity rover, another absolutely glorious shadow photograph. They're just so beautiful, just purely there because they look nice. But this is Victoria Crater on Mars, and this is another one. It's a really big crater. This is from the Mars Reconnaissance Orbiter, and depending which way round you look at this crater, this too can look like a dome rather than a crater, or look like one of the volcanic features on the surface of Mars. Now, one of the things that Mars is famous for is sand dunes, the dunes that have been shaped by wind over millions of years, and they create this beautiful kind of rippled surface. But one of the things that it can also do is produce these really weird optical illusions. Now, the Telegraph reported this story a number of years ago, saying that there are trees on Mars. Now, we all know there are definitely no trees on Mars, but this picture really interests me because when you look at these black lines up at the top of the picture, it's really obvious that it's just something has rolled down one of the sand dunes and exposed some darker material underneath. And it's the same here. You can see that there are kind of slumped areas there where you've just got darker material that's showing through because something has slipped downwards. But the minute you come down here, it's hard to actually see that that's what you're looking at. It really does look like tree trunks standing up. I mean, if these are trees on Mars, they've undergone some catastrophic event that has removed all of their canopies, but they really do look like they're sticking up from the surface. So I think it's really important. The press love to share stories like this because they know they're nonsense, but they get clicks. But it is really important to keep in mind that you might not be seeing what your brain thinks you're seeing when you're trawling through the archives of these pictures. Sorry, Evie turned my slide for me. And an example of this, Stuart Atkinson loves to process images taken by the Mars rovers. And this is a perfect example of how your brain can completely trick you. This is an absolutely stunning landscape here where you've got all these kind of windswept sand dunes and all of those lines. But over here, this just looks like a plate of sand just hovering in midair. It's just really weird how strange this landscape can look when you do a little bit of processing on it. And actually, even the raw data itself can be a bit weird. So definitely worth bearing that in mind when you're looking at the pictures that we see from the next Mars rover. And it seems to be more of a problem actually with orbiters rather than stuff on the ground, because you're seeing it from above and everything just looks a little bit strange from above. Let's have a quick trip to Jupiter. This is a picture that Mark and I took a few years ago, and this is Europa, and that's where I want to focus this bit. This picture is not taken by us, obviously. Europa is a really interesting one to study, and I actually watched another talk the other day about the upcoming Europa Clipper mission, which was really interesting. From like looking at it as an entire moon or an entire world, it looks kind of fairly flat and like there's not much going on apart from the weird kind of scarps. But if we actually look at this region here, this is called Connemara Chaos, and this is a region that I studied when I was doing my Open University course, looking at the ice rafts on Connemara Chaos. And this is such an interesting part of Europa, and we still don't fully understand how some of these features form. But basically, Connemara Chaos is just one region where there are loads and loads of these crisscross features, and some of them kind of look like pairs of ridges. Basically, what's happening here is that Europa basically has a lot of tidal heating because it's got an elliptical orbit around Jupiter. It's tidally locked and it's expanding by about 30 meters every 3 days. So that stretching and compressing causes tidal heating beneath the surface. And it's widely believed there is a liquid saltwater ocean underneath the surface. And basically, it's thought that there are regions where that pockets of heating just get focused and these little areas will melt. So you get all of this melting and then these rafts kind of spread apart a little bit. You also get regions where these huge like ridges get pulled apart and turn into kind of flat, kind of strange features. They don't know for sure that's how they form, but it's over millions of years it's been frozen and then thawed and cracked again and then refrozen, and it gives rise to this very, very chaotic terrain. One of the Galileo space probe was looking at some of these features up close, and basically you can see that there are these huge ice cliffs here, and you just wouldn't think that this was a feature when you see the planet from above, see the moon from above, because there's no real craters there. That it just doesn't have features. It's a very young surface. It's obviously been undergoing some kind of resurfacing over the period of the solar system's lifetime. This is another picture from the Galileo space probe. This is 75 kilometers from top to bottom, and the Galileo probe was orbiting, exploring the Jupiter system for 8 years. And the great thing that you're able to do when you send a probe to another world is basically study the terrain under different lighting conditions. Because of the way that the solar system is arranged, when we have our planets at their best, they tend to be at opposition. Unfortunately, that means they're lit from above, from our perspective. So any kind of features kind of get wiped out a little bit, even if we could see the features. So basically, we don't have the luxury of looking at the chaos terrain under a low lighting angle, even if we did have a big enough telescope. And this is something that is one of the main reasons it's really useful to send probes there. One of the things that this probe found was that there were ridges and icebergs that were over 5 kilometers in diameter, and they had heights of like up to and over 100 meters. And that's just not something that they expected to find when they went there. So these space probes are just so invaluable to our understanding. Similarly, we had the Cassini space probe around Saturn. Now, Saturn has got to be all of our favourite planet. The ring system is just so gorgeous. Many of the planets in the solar system have rings, but none of them stand out the way that Saturn's do. Now, Cassini was there for a number of years, from 2004 till 2007, and that again gave us the opportunity to look at Saturn under different lighting angles and compare. This picture is here purely for the fact that Saturn, the actual main planet, is casting a huge shadow across its rings. Looks like the rings have got a massive bite taken out of them, but also the rings here are casting a shadow onto the surface of Saturn. I never get bored of looking at Cassini imagery. It's just so beautiful. And this is another one where you've got the shadow of the rings being cast on the planet below, but they look curved because of the curvature of the planet. Just so gorgeous. And seeing the rings from this angle where they're so thin, then these bits down here are actually the shadows of the rings being cast onto the planet below. Just in terms of shadows, this is just pure heaven to go and have a look. And this picture is just extraordinary because it's looking through Saturn's rings at a banded surface, looking at shadows of the rings then being cast onto the banded surface. And no sooner do I get my head around what I'm looking at here before my brain goes, no, don't get it again. There's just all this really weird crisscross thing going on. It's so gorgeous. But one of the things that was really a big source of surprise during this was when we started to find features in Saturn's rings when we were looking at them under this low lighting angle. Now you can see from this photograph here, there's something here that is casting a long shadow. Now obviously you need a low lighting angle in order to find that, but basically they did exactly the same maths, the same way that we did on Europa looking at the ice rafts, using the sun angle, the shadow length, and then they were able to calculate the height of those features, just using exactly the same equation that I showed you before. Now it was always thought that Saturn's rings were about the thickness of a two-story house. What they actually found is that there are regions within Saturn's rings that are as high as the Rocky Mountains, and that was just mind-blowing. We could never have known that if we hadn't had the opportunity to study the rings under a low lighting angle like that. And these photographs are just so gorgeous, where you've got these kind of edge features along the edge of the rings there, casting these really long jagged shadows. Now obviously under a low lighting angle the size is exaggerated, but they took that into account and looked at it under different angles. But these low lighting angle pictures are just absolutely beautiful. And this is Daphnis and some wave edge wave shadows along the edge of one of the gaps in the rings. So beautiful. And then I had to include this as well because this is a shadow of Mimas being cast onto the rings, while you've got the other kind of jagged shadows from the edge of the ring as well. So having Cassini there and looking at this under those lighting angles totally revolutionized our understanding. Equally, when we went to Pluto and Charon, this was amazing when we had the New Horizons mission, because until that point, this was the best photograph of Pluto that we had. 2015, we suddenly had this, and it just turned everything we thought we knew about Pluto on its head. But one of the things there, when we look down here, there are all of these rugged highlands, and there's some beautiful shadow pictures that came from New Horizons. And also these hummocky regions here and the shadows between all of these really weird kind of geological features that are on the floor in the lower lying areas. And equally, when we had Rosetta going to visit comet Churyumov-Gerasimenko, we found features that we were not expecting to see on a comet. There are huge craters here. There's loads of high regions, low regions. And again, because we've got the luxury of looking at it under different lighting angles, not only do we get to see the outbursts of gas and dust from the comet, but we're also getting all of those lovely shadows. And I just love this picture. It's just incredible to me that we're seeing a picture like this of this deep dark shadow being cast on the surface of a comet. We just don't expect to see this on a comet, and it's just so beautiful. So I had to squeeze it into this talk as well. Now I'm going to finish off by talking about something else that's important to keep in mind when we're looking at shadows and patterns, and that's something called pareidolia. And that is a psychological phenomenon that I think is unique to humans, but it causes us to see patterns in a random stimulus, and quite often that means that we assign human characteristics to objects that are inanimate. And I am one of those people that doesn't really see shapes in clouds very well, but even I can see, this is a picture by Peter Chappell of a geyser, and I think it was in Iceland he took this picture. Clearly looks like the profile of a human face, which is pretty creepy, to be honest. And throughout history, kind of superstition and legend about the things astronomical have played a role in pareidolia as well. And we see this very often with crepuscular rays in religious artworks. It's really common whenever you see an angel depicted somewhere in any kind of illuminated scripts to do with religion. Angels always have those kind of beams of light coming out from them. It's kind of easy to see how people, like way back in time, would have seen a gap in the cloud with those rays coming out and must have thought it was a visitation from an angel. I'm not remotely religious myself, but I can totally see where that imagery may come from. And I know some people call crepuscular rays fingers of God, and they are pretty spectacular to look at, but that is where you see those depicted quite often. But also there's a lot of superstition and legend around atmospheric optics, and particularly when you get a multi-halo display like this, which we rarely get from the UK. One of the things we do get a lot of is sundogs, which are the brighter regions here that I've got a photograph of in a second. But what you can also get are sun pillars and also fragments of a parhelix circle, which give you a cross shape coming out from the sun, in addition to the other things that you see around the sun as well. And that has led to religious significance being placed on atmospheric optics. So this is a more common picture of a sundog, some pair of sundogs that we might get from the UK. There's a hint of halo there as well. Now, the sundog's proper name is parhelia, from the Greek Germanic word meaning beside the sun. And the earliest artistic representations of them are in the first ever illustrated Bible, and that's the Nuremberg Chronicle. And this is absolutely no doubt in my mind whatsoever that these pictures, what they have drawn here, is where somebody has seen some atmospheric optical thing where you've got sundogs either side of the cross shape, and it's very clearly being depicted as the Holy Trinity. So you can totally see where they've got that from. And sundogs are sometimes called mock suns as well, which is more what we're seeing here, like mini suns either side of the sun. So definitely that is atmospheric optics being used to depict religion again. But in terms of shadows, one thing that I've created one artificially with my car headlights in the fog, but one thing that is also wrapped up in myth and legend is the Brocken spectre. And this got its name because the Brocken is the highest peak in the Harz Mountains in Germany, and that peak is shrouded by mist for 300 days of the year. So any mountain climbers or hill walkers that venture up there, if you've got the sun behind you rising in the sky behind you, you can get what's basically like the equivalent of a corona but seen from the other side, where you get these kind of pastel coloured rings coming out from your head, but leaning up to that shadow is this really long grey shadow, which must have been terrifying to people who didn't understand what they were seeing. So I've made this myself with car headlights, and it felt a bit creepy, but if I was stood at the top of the hill and saw my shadow kind of going out so far ahead of me like this looks like, I think I would be fairly spooked, even though I know what it is. And this is basically also tied up with the big grey man of Ben Macdui, or sometimes known as the Scottish Bigfoot. And this is basically where there were many reports of terrifying experiences during mountain climbing. And one thing that happens when you're up in a mountain or walking through hills is the wind can do some really weird things. And add to that the echoes of your crunching footsteps on ice and groaning sounds just from the way that the wind is doing it, and then suddenly you're faced with this huge grey shadow apparition. You can see that where this big grey man of Ben Macdui has come from, and basically Ben Macdui is like the equivalent of the Harz Mountains in Scotland. So this is a really interesting kind of bit of folklore for me, because this is clearly based on a shadow. Also, we like to assign human features to things, and one of those things is the man in the moon. And there are many different ways that people see faces in the moon. I have never been able to see any of them, but when I was at school and people talked about the man in the moon, I was terrified, even though I can't see it. But this piece of art from somebody on DeviantArt has kind of preferentially enhanced the regions that are supposed to be the face. Even armed with that, I can't see it in a moon picture at all. But also, I showed you before the face of Albertagnus, and quite often we assign human form to these clair-obscur effects on the moon, and that looks just at the right phase of the moon, just for a short amount of time. You've got like a side profile of a face being cast onto the crater floor. Also, the eyes of Clavius, one of the biggest craters on the near side of the moon. If you get it at just the right angle where most of the crater is in shadow, the craterlets have got a higher rim and they just catch the light and look like a pair of eyes peeping out at you again. Also, this assigning human characteristics to things has happened over and over again with the press when looking at pictures of shadows taken by the Mars rovers. And this is one example of that. The top quality scientific journal, the Daily Express, posted this picture apparently of an astronaut working on the rover. And this is another one where apparently the Metro was claiming this looked like a man working on the Mars rover. Now, the trouble with these things is when you're looking at a photograph of a barren landscape with no known features there, you've got no concept of how big that thing actually is. Now, that shadow is actually caused by this particular robotic arm. It looks nothing like a human, but the Mars rovers are quite big, but the majority of the things that people see on other planets are just not big enough to be a human. They just really aren't. So it's really important that we just take this stuff with a bit of caution. I mean, you guys know that there are no astronauts on Mars, so I'm preaching to the converted. But this was another thing when over the years, when there has been surveys done over of the Cydonia region of Mars, and more famously the face on Mars, and this was originally imaged years and years ago by Viking 1, and this does kind of look like a mask, like maybe a Friday the 13th Jason mask or something like that. But actually, when you go back, and when we went back again with the Mars Global Surveyor and actually did a high-res scan of that region, first of all, it's a lava dome. It looks nothing like a face. But also, just note the size here. This is 3 kilometers by 3 kilometers. So if somebody was going to actually go to the trouble of carving an entire rock into a face, I don't think they'd have done it over a rock that measured 3 kilometers in every direction, because that's a lot of chiseling going on there. So, and I like this picture where somebody is, the astronauts have gone there looking for the face on Mars, and when seen from the side, it's basically a jagged lava butt and looks nothing like what they're expecting. The Mars rovers have just been full of people finding human form, and one of those is the woman on Mars. In case you can't find her, I'll help you. She's there. This is basically about 20 pixels. It's just a bit of shadow, and this thing could be 18 feet tall, it could be 18 kilometers tall, it could be 18 inches tall. We just don't know. There is nothing in the foreground at all to give us a frame of reference here. It's just a random look that the shadow kind of vaguely resembles human form. I would never have noticed that if it hadn't appeared in an article. There's also a mermaid on Mars, apparently. She's probably about 50 pixels in size, so she's a little bit bigger, but still very, very tiny. And I think somebody did a takedown of these, and each of these things, I think, ends up being about 15 centimeters in height, something like that. You know, you really have just no concept of the size. And there's an iguana on Mars, in case you'd missed that big news as well. That does kind of look like an iguana, but again, is this iguana 18 kilometers across, or is it a tiny micro iguana? We just don't know. We've got nothing to help us out with that at all. Now, as well as the assigning human characteristics thing, shadows in space has led to a lot of architecture conspiracy theories. And for decades and decades, people believe they're seeing man-made structures on the moon and other planets around the solar system. And I get interactions from architecture conspiracy theories quite regularly on Flickr. I'm curious. I actually almost want to engage with them to find out what it is they think they're seeing in my photographs, but I know that's opening an entire floodgate of batshit bonkers that I don't really want to get involved with. But this has been on the moon as well as on Mars, where people have just, like, a lucky lighting angle has given rise to, oh, there are pyramids, they must have been there, they've built pyramids. Again, we have no idea how big this pyramid is. It could be a tiny boulder that just happens to have a sharp edge that makes it look like a pyramid. No idea at all. And also Copernicus and Tycho have these slump terraces, as do many other craters, and people try to say, oh, that can't possibly happen naturally, it must be quarries. These are the sorts of terraces that you get when something's been quarried for rock. No, they're not. If you've done any basic sort of studying of how craters form, the impact initially, you get a kind of rebound if there's a central peak there, then obviously the stuff around the edge is weakened, and then over time they just slump down. It's a really, you see it all the time. If you try and make a big sandcastle and the sea starts to come in, you get slump terraces happening when there's an instability there. So they're not. What I find very amusing, you saw the photograph I showed you before of Tycho and the boulder on top of Tycho. The entire lunar surface has been imaged by the Mars Reconnaissance Orbiter in exquisite detail, yet this is the picture everybody still brings out, which is a really old picture full of loads of very weird imperfections because it's an absolutely ancient photograph done on film. And there's a castle apparently that's 9 miles above the moon, but the conspiracy theories like to tell you that this is a castle. I mean, it's all just utter nonsense. It's all just natural features. But whenever you try and reason with people, these are the pictures that they're wheeling out. This is what the castle on the moon looks like up close. I mean, it's just, I don't know what that is. It's obviously just some kind of lens imperfection. But why would you still, surely this region has been imaged in greater detail. Just go back and look at it and see what's actually there. And also this is apparently a city on the moon. All I'm seeing is just some highland regions. This is such a bad photograph compared to what we're capable of getting with a moderate telescope from the ground, let alone what the Lunar Reconnaissance Orbiter's been doing. So when we're faced with pictures like this, why do people still wheel out the old stuff? Well, basically because this proves that they're talking nonsense. So I hope you found that interesting. If anybody has any ways that I can improve the maths that I showed you tonight, feel free to hit me up because I'm not a mathematician. If any of you do want to have that kind of crib sheet of how to go about doing the shadow calculations, just let me know and I'll email it to you. And 27 things in the chat, crikey. Go through the chat.
Fantastic, Mary. Covered it from sort of like really high technology imaging of Saturn from Cassini and the moon with the reconnaissance mission, as well as sitting there looking at a picture and measuring in your own home and producing some fantastic results. Absolutely brilliant. It amazed me about the crepuscular rays being parallel, and I've never thought of that before. Of course, they have to be like meteors, isn't it? It's exactly the same effect. But anyway,
yeah,
anybody got any questions?
It makes my brain hurt. The fact that those rays are parallel makes my brain hurt, even though I know it's a fact.
It's obvious when you think about it, but yeah.
Yeah, it's just crazy. Somebody just mentioned about the really weird thing about a Brocken spectre is that it's only visible to you where you're standing. And that's actually the case with all atmospheric optical effects, because the things that you're seeing with atmospheric optics are not a fixed thing in space. So whether it be a halo or a rainbow, the one that you see is focused specifically on your eyeballs and is a different rainbow to the person standing 12 inches away from you. And it's just the way that the ice crystal is refracting the light and it focuses on your eye. So, and I did this when we had a lot of fog earlier this year, and actually at the end of last year, I took my car out to one of the quiet country lanes near here, stood in like behind the car, you can just see fog and car headlights. The minute you walk in front of them, a huge fog bow appears, and you step to the side and it goes again. And it just really shows you that basically this is not a fixed object. It's not a real thing. It's not a physical thing. And it's one of the things that I love when I do atmospheric optic observing, is that there are gazillions of tiny ice crystals have focused their light on my eyeballs, and what I'm seeing is unique to me. So I think that's really cool. So yeah, the long-winded way of saying yes, nobody else's Brocken spectre is the same as your one.
Brilliant. Any questions for Mary? Anybody else?
Oh, I'm just looking, somebody's saying there are square trapdoors in lunar craters. Yeah, there were artifacts from JPEG compression. A lot of the people that come up with these conspiracy theories don't understand anything about imaging in general. They don't understand image processing. They don't know how cameras work. Hot pixels and cold pixels, they think they found something exciting. They haven't, you know, it's... I try to help people and educate them.
There are like hairs and things on some of the reproductions where they're like, oh, look, that rock's lettered C because it's a prop that was put in position, and things like that. It's just madness.
Crazy.
That was a great talk, Mary. Really enjoyed it. Thank you.
Thank you. I'm just trying to go through and see if there are any more questions that I've missed on the chat.
Yeah, one thing I've been trying to find out, Mary, and I've really not found out the answer yet, because the moon has libration and all sorts of things like that and wobbles backwards and forwards. I've never found how that angle changes of sunrise, so whether it changes much in azimuth so that the shadows are pointing in slightly different directions at sunrise on different sunrises.
They definitely would be.
It must do. So so one of the things I'm going to try and do is to just take as many pictures as I can and see if I can see if there's a difference. But I've never found out an actual. Well, it varies by X amount of degrees or bits of degrees. I've never found that information out, and I'm still trying to find out.
I mean, it might be something you can do with the Lunar Terminator visualization tool. You can certainly see how the sun angle's affected during one entire month. You can just skip forward day by day and just see if that gives you any clues.
Yeah, but it'd be from sunrise to sunrise. So if the next sunrise is from a slightly different angle, a bit like ours, it changes throughout the year. It goes from the southwest to the northwest for sunset, and northeast to southeast for sunrise throughout the year, and it varies quite a big angle from the Earth. But the moon, because it wobbles backwards and forwards, although it may not vary quite as much as ours, it must vary.
Yeah, it would do.
From sunrise to sunrise or sunset to sunset. So.
Yeah, that'd be interesting to find out. In terms of shadow calcs, it won't actually matter because you're still measuring the shadow. But in terms of where the sun's rising, it'd be really interesting to see the difference.
Yeah.
Can you not go to the moon's surface if you are using stellarium? Is there not a way that you can go to the surface of another planet in stellarium?
Oh, there is. Yes, you can. You just go to, don't you? And then you select your latitude and longitude, and you can put yourself anywhere on the surface. Yeah, I could try that. Okay, yeah.
It's my go-to because it's a visual thing instead of a maths thing, so I can actually look at where it is rather than try and measure it.
And you can fast forward time for the next sunrise and see if it's varied from where you were standing.
Yeah, that's be interesting to do.
Yeah, give that a go. Yeah, John's just put a comment in there. Yeah, that's right. Yeah, I realise what it is and how it varies, but I've never found an actual figure for how much it does vary.
Someone was saying about seeing a Brocken spectre from an aircraft. It's slightly different. You're seeing a glory, which is the concentric rings are the same thing, but you get the shadow of the aircraft in the middle. But yeah, what's really interesting that John has said there is that if you look for pictures of glories with an aircraft shadow, if a pilot has taken it, basically the center of those concentric rings will be from the observer. So if the pilot took a picture, the nose of the aircraft is at the center of the rings, whereas if somebody sat at the back of the plane took the picture, then that's at the center. So it's really interesting. And if you ever there's actually a really cool picture of this on the AT Optics website. If you go out and see a Heligan shine, is it Heligan? Yeah, Heligan shine, where you can see a halo around your shadow on a frosty morning or in the dew. You can take a photograph of it and with your camera near your head, and you'll see the halo around your head. If you hold your phone out to the side and take a picture, the halo is then around your hand because the lens is the bit that's at the center now. And I think it's amazing. And again, just shows that it depends where you're standing, what you're exactly going to see.
Yeah. Any other questions from anybody?
Just put one in. Sorry, I've just put one in there. I'd like to know more about this lunar determination tool, really, to be honest.
Okay, I will just let me go and get my notes open, and I'll drop the link where you can download it. It's from GitHub, but you don't have to do coding to get it from there. I'll get my crib sheet up, and then I will.
You pop it in the chat, Mary.
I will do, yeah.
It saves the chat, so what I'll do, I can grab that and pop it on the webpage tomorrow.
Yeah.
Okay, great.
What I can do actually as well is just put all of that help sheet onto Dropbox and drop the link into the chat as well. I'll do that before I leave, then you've got it.
Great.
And say my maths won't be absolutely perfect because I am not a mathematician and I do everything I can to try and avoid
good idea
doing maths.
Yeah.
Okay, I'll just look.
Having seen your atmospheric optics and things like talk a few years ago, I think we'll have to get you back to do that one as well, because that's a really interesting talk too.
It's an unusual one. A lot of people kind of might not think of that as an astronomy thing, but it's so interesting, and it's a subject that you can get very bogged down in the physics of if you want to. Okay, I'm just going to put the GitHub link to download that termination tool. It's really useful. It's a very, very useful tool.
Excellent. Thanks, Mary.
It's very crude interface, but it does the job. It does absolutely everything you need it to do. So it's great.
Definitely.
I'll have to get my grandson to do the angle of the stick in the ground.
That's a really great one to do, because it really shows how the shadows change over time. I mean, I didn't work through how you can use the shadows to actually calculate the height of something tall, because it's just a ratio thing. You just scale it up, and the talk was getting longer and longer, as always happens with my talks. So I took it out, but you can just stand next to a tall thing, measure the length of the shadow of a 1 meter ruler, measure the length of the shadow of a tree, then just multiply one by the other, and you get the height of the tree. It's quite a fun child activity to do.
Yeah. Okay, thank you.
Excellent. So, any other questions for Mary?
I'm just copying this to Dropbox while I talk to you. Not very good at multitasking.
Well, that's certainly been absolutely fascinating. I'd love to talk. Brilliant.
Okay. Yeah, well done.
Thank you. Okay, I'm just going to drop that Dropbox link. Oh gosh, that's a very horrible long link, but you can run it through Bitly or something. An ugly link, but it takes you to my hopefully not too ugly maths.
I'll pop them on the web page in the morning.
Good.
Excellent. Okay, we've certainly got our money's worth tonight, Mary. Thank you very much. Very comprehensive talk.
So sorry, I always talk for too long, but
okay, so if nobody's got any more questions, I'd like to thank Mary for a wonderful talk tonight.
Just a quick thing, Dave. Do you want to put a note on about that I put in the chat about why Mary was doing it in radians?
Oh yeah, did you look back? I saw that.
Excel actually works in radians. If you do it in your calculator, of course, that works in degrees, so you don't need to do radian conversions.
Okay, I was doing all mine in Excel, so
it's one of the things people mess up. I could tell you a very long story about a firm of consulting engineers who messed it up, but I won't.
Oh, I've heard of some of the disasters when people have used imperial instead of metric, and
well, they lost the Mars probe because of that, didn't they?
Yeah. Never lived that one down.
No, never. Yeah. Well, that's been brilliant. Thank you very much, Mary, again. Absolutely amazing. Again, thanks to everybody for coming in this evening. Yeah, you folks are speakers that make the club what it is. So thanks very much, everybody.
Thanks for having me.
Brilliant. Thanks so much. Okay, so last thing to say is keep safe, keep well, and as Roger says, keep looking up. See you, folks.
Okay.
See you next time. And those who are coming in on Thursday. Okay, see you then. Bye-bye.
See you Thursday.